All right. So no pictures allowed. Yeah, so I'm glad to be at a summer school. I think summer schools are really important. Otherwise, people tend to get educated in this field just by reading things on the internet, which is okay, but not ideal. Right now, we're in an era where neural nets have returned. I was in one of the first summer schools of neural nets in the middle of the 80s. Some of you weren't probably born. And there was kind of a lot of the hubbub right now that maybe we're discovering great things and could change the world. I was always suspicious about that. I think we're very much pre-Newtonian. We don't really have the concept yet about understanding intelligence. I still feel that way. I don't think stochastic gradient ascent in layers of parameters is going to give us intelligence, which is my view. It'll give us things that mimic intelligence or that do mappings that are useful in building intelligent systems, but that's far from deep understanding of intelligence. And the other thing that was happening in that era was that it was highly empirical. So that's good. You need it to be empirical. You need to really try things out. But at some point, just being empirical is not very satisfying intellectually. And especially if you think about what do you deliver to the next generation. You delivered, here's some algorithms we tried out and they worked. And that phrase, it works, leaves me a little cold. Yeah, I'm glad you tested it out, but I don't get any understanding from that phrase. So there should be people doing that, and there are now probably hundreds of thousands worldwide doing experimental things with neural nets, and that's all great. But there needs to be a subset of other people who are doing foundational work and trying to think about what's the new mathematics we need, how can we extend what we had in the past, and take this field seriously as a mathematical discipline, and see if we can develop something robust and rigorous and kind of exciting in that side. I personally don't be particularly interested in having a robot walk across, and some people get super excited about that. I get much more excitement about a theorem. I think so. So anyway, I hope that some of you, at least in the audience, feel the same way. There's lots of math to do, and so I keep kind of moving around the field looking for new things to do. And I haven't been an optimization person, really. I've been kind of watching colleagues and friends from a distance. But the last few years, I've gotten more interested in optimization. I'm always interested in it, but have more ideas about it. And but I'm not a real guru, I'd say. And so I thought that's actually perfect for a summer school, because I can teach stuff that I don't feel that I'm quite a guru yet, and therefore we all can kind of learn. So I'm going to, in fact, do a little bit of stuff on the board at the beginning. And normally, if it was a topic I was a guru at, I could just go up to the board and write out theorems and proofs and nothing. But I'm not going to be able to do that for optimization. I'm not quite there yet. Anyway, by the end of this lecture, or certainly by next lecture, we're going to get into some fairly interesting mathematics. And what's going to happen is that at some point we're going to go from discrete time to continuous time. And that's going to be new and different. Almost all the literature on optimization has been in discrete time. And almost all the ideas are convexity-based or bounding step sizes, but you're never really thinking about underlying dynamics. At least that's not been the classical way of going. And I'm going to argue that to get a foundational understanding of some of the core concepts of modern optimization, particularly the notion of acceleration, which is really key, it links lower and upper bounds, you have to go into continuous time. So that's kind of what some of the buzzwords in the title here have to do with. Variational means just turn a integration problem into an optimization problem. And then we're going to see related concepts that are Hamiltonian. And the word symplectic is probably the key word here. So this is a way to integrate certain classes of differential equations. And it hasn't been brought into the field of machine learning at all, except at one little spot. There's something called Hamiltonian Monte Carlo. And inside of that, there is a symplectic integrator. It's the only place I know of where that set of ideas are probably brought in. So I'm going to teach you a little bit about what symplectic integration is and why I think it's actually deeply important. It really, roughly speaking, is the way to think about acceleration. How many of you already know what Nesterov acceleration is? So I just set my tone. Okay, only about a third of you. That's pretty good already. That's bigger than most audiences, but still not big enough. So part of the goal today is to let everybody really know what this important set of concepts are. So just kind of a little history on optimization. Of course, it's hundreds, if not thousands of years old. I'd say by the early 80s, when kind of I was a grad student, it was viewed as basically finished and dead as an academic discipline. That really good algorithms had been developed for both the constrained and unconstrained case. Their rates were understood in a wide variety of situations. Lots of numerical constants were understood, and these things worked in practice, and it was there was not much more to do. And as in many fields, when people start saying that, you know you're about ready for a revolution. And that's what happened. So one of the first things was interior point methods, which was at least a mini revolution that surprised people that you could do things that weren't viewed as possible. But probably a deeper revolution was this one started by people in the Russian school, Nemirovsky and Nesterov are the names most associated with it, Polyak and others, who discovered lower bounds in optimization. Okay, so lower bounds, when you start having lower bounds, you start to have a more deep appreciation of what a discipline's about. Because you're really able to say something about what's the best you can possibly do. And once you've said that, you sort of must have had some understanding. Okay, so in fact, optimization hadn't had any real lower bounds, or not many. You write down an algorithm, conjugate gradient or something like that, and you analyze it. And you show in some class of functions, here's its rate. So that's already pretty interesting. But it's somehow just a rate. Then the next question is that the best rate you can achieve? Well, it obviously depends on the class of problem. So you have to think about that. What class of problem am I going to get an interesting theory? So Nemirovsky and others did that in the 1980s. So they came up with a kind of a general way of thinking about lower bounds. It's not the only way, but it is a good way. And it gave you lower bounds that could be met by actual algorithms. And that's not that common. In some fields, you're able to do that. So I'm really a statistician at heart. I don't call myself a machine learning person, actually, because I think statistics is the bigger, broader discipline, decision-making under uncertainty. And statistics, I think I'm proud to say, has tons of lower bounds. And they're often pretty good. So, Kramer-Rao lower bound is an old one. But all the empirical process kind of bounds are, lots of lower bounds. So there's other kind of concentration of lower bounds. Some of them are borrowed from information theory, which is another field that has lots of lower bounds. It's focused on easier classes of problems in some sense. And then computer science has some lower bounds, but very few, and most of them are pretty vacuous. They're far below what are known algorithms called, exponential gaps. So in some sense, that's because computer science is newer, but probably also because it's, in some sense, trying to solve the mother of all problems. What is computation in some very, very general sense? So you don't expect to get very tight lower bounds. And one of the historical things that has happened is we've tried to develop a more theoretical approach to computation meets statistics, is that we go around looking for lower bounds. And those from computer science and complexity theory just haven't turned out to be very useful. On the other hand, somebody at some point discovered Nemirovsky and discovered the lower bounds from optimization theory. Okay, so optimization has played a crucial role in the last 20, 30 years, partly because of that. Not just because of the algorithms that are sitting there, but because finally we have a complexity theory of computation. It's not the Turing type, it's a different type, but it's a notion of computation which is relevant to us. We like optimization. Now, it's not everything. Obviously, there's going to be ideas needed to do us beyond just optimization, but it's a good starting place. And so that's some of the context for this talk. We'll be talking a lot about lower bounds, a lot about Nemirovsky, and algorithms that achieve lower bounds. Okay, so see, I'm not quite ready to get those slides. So what I'm going to do is a little bit of stuff on the board here. This is perhaps stuff that Subrit Shah has already done, or somebody else, but maybe notation or just reminding you is a good thing to do. So let's start talking first of all about rates for optimization problems. Between blackboard and whiteboard, what do you mean? Oh, there's a blackboard underneath here? Oh, I see, that's neat. I think what I'm going to do is just go over there. I'm not going to use a lot of board space. Let's use it. I am old-fashioned. I'm really tempted to use that, but I think I'll stick with it like that. So let's just talk about getting rates for convex problems. So if I have an arbitrary convex problem, so it's not necessarily smooth. Okay, so it's convex, looks something like that, but it's not necessarily smooth. So you can have kinks in it. All right. And suppose that I'm going to do gradient descent on that, just classical gradient descent, okay, with a particular choice of step size. All right, so what's the rate for that problem? Does anybody know? If I do k steps, how close am I to the optimum? It's 1 over square root of k. All right, so k is going to be the number of steps I take in these problems. So that's our complexity parameter. And we're going to be interested in, after k steps, how close are we to the answer? Okay, so it has to go down as k gets larger. So it's like 1 over k or square root of k or something, or maybe e to the minus k would be nice. Right? So we're going to be getting rates like that. Things like 1 over square root of k, 1 over k, maybe 1 over k squared, maybe e to the minus k. And we're going to be interested in where those rates come from and are they the best you can achieve. Okay? All right, so already for gradient descent on an arbitrary convex function, that's kind of interesting because it's an arbitrary function. Okay, so I mean, if the function happened to be just like that, that's convex, and I've got the minimum immediately. Where all points are minimum, so I don't have to do anything, so I need 0 steps. So obviously this is a little more of a worst case story. It means find some function in which you achieve a rate that's as bad as possible, and that rate will be 1 over square root of k. There exists no function where you can't get to the optimum in that rate. Right? If we go up to smooth functions, and I'll define smoothness here in a second, but we can't allow kind of an absolute value kink anymore. What's the rate at that point? Well, you might imagine it's that, and you would be correct. Okay. Right? What if it's smooth and strongly convex? So strongly convex means you can lower bound it by a quadratic. So these kind of things are not allowed. What's the rate there? Can't hear you. Which one of those is linear? Yeah, that one right there. So we hopped all the way up to there. We skipped over that guy. So is that guy interesting? Right? Well, it will be, certainly. Okay, so let's talk a little about how to get these rates. So what about stochastic stuff? First of all, that's just gradient descent and no stochastics. So what about stochastic stuff? What if I've got a non-smooth but convex function? What's the rate there? Yeah, back to here. Clearly. What if I add smoothness? Same. Doesn't get any better. Okay, so it already starts to get in. Okay, so let's start talking about how to get rates. So let's just take a function f that's going to be convex but not smooth. Let's let the range or the domain it lives on be called script x, and let's let that live in a ball of radius r. Okay, so we're going to be Euclidean work here today. Almost everything I talk about being generalized in a whole bunch of directions, including Banach spaces and dual norms and so on and so forth, but we're going to be really simple and concrete here today. So we're going to talk about Lipschitz functions, and one way to talk about them, it's a little different than just Lipschitz, is to insist that the gradients or the subgradients of the function have an upper bound on their norm. Okay, so for all x in this space and for all subgradients at any point x, I want that the norm of the subgradient be upper bounded by something which we'll call L. Okay, so you hopefully all know what a subgradient is. A gradient is something that lower bounds a convex function here, if you use that as its slope. And a subgradient just generalizes that to places where you have discontinuity points. So here, any slope in some set of slopes from -1 to 1 is a subgradient. Okay? It gives the lower bounding property when I use it as an inner product. All right, so that's enough setup already to now take an algorithm. Here's my algorithm. It's going to be gradient descent. X at j plus 1 is equal to x at j minus, I'm going to step along the gradient by an amount eta. And we're going to allow ourselves to have subgradients. So I'm going to call that g sub j, which lives in the subgradient space at point xj. Okay, so I keep going downhill. If I hit a point of discontinuity, fine. I just take any one of the subgradients at that point and keep going. All right, so here's a theorem which is one way to express these things, is that let's take f, not at the latest point, but just let's take an average of all the previous points. So j equals 1 up to k of x of j. Okay, so just average all the points we've gotten to so far. Now, if you know this field a little bit, you'll know that that's often the best way to analyze algorithms. Get better rates doing that than just taking the last point, in theory and in practice. So let's look at the discrepancy between that and where we want to be. So x star is the optimum, an optimum. Okay, so that is upper bounded by something which goes as 1 over square root of k. And here we can even be more precise. We have r times L times square root of k. All right, so most of these theorems have, you know, rate, and they have there's constants here, and these constants appear in very, very simple, nice ways, pretty typical, okay, kind of natural. Maybe they're get squared occasionally, but often they're just the constant. So let's do the proof of this. So first of all, let's just use convexity. So proof. So f at x star. If I evaluate a subgradient at where I currently am, then I'm going to get a upper bound just as I drew over there. So if I take the subgradient at point xj, and I use that as the slope, x star minus xj, then I get an inequality, and that's just as I've drawn over here. Okay. If I then rearrange that, I can write f of xj minus f of x star is less than or equal to gj transpose xj minus x star. Okay. So on the left-hand side, we're already starting to get a discrepancy of some kind, and then you can sort of see if we sum this over j, I'm going to get something like this, and I'm going to use Jensen's inequality to bring the sum inside of f, and so on the left-hand side, I'm already kind of done. All right, so on the right-hand side, I've got to do some work, right? And this is very commonly the case that you have an inner product sitting there staring at you. What do you do with inner products? Well, they kind of bring two things together, and you want to decouple those two things typically. Right? And when you decouple them, you can start to analyze them separately. Right? So there's different ways to decouple things. One way of decoupling things is to use Cauchy-Schwarz. So it's probably the most useful inequality you ever have. And I hope you all know what Cauchy-Schwarz is. X transpose y is less than or equal to the norm of x times the norm of y. I just decoupled x and y in a multiplicative way. That may be useful for me and is useful in lots of situations. There's also situations that I want to decouple things in an additive way. Okay? And there's something called the Finchel-Young inequality, which if you haven't seen that before, go to Wikipedia. Very, very useful. So we're going to use that one here. It decouples things in an additive way. And this particular one actually is the one we're going to use here as an equality. So it's 2 times x transpose y is equal to x norm squared plus y norm squared minus x minus y squared. Okay, so it's just elementary school math. Take this thing and let's expand it out. So Finchel-Young basically generalizes that to make this an inequality, and you can have a 1 over epsilon and an epsilon in your two sum pieces. So have a look at that. We may in fact use it later. Okay, so let's keep making progress. So where's our algorithm? Here's our algorithm right here. And this algorithm relates G to the discrepancy between X at 2 different steps. So if I solve for G here, G is equal to XJ plus 1 minus XJ divided by eta. So let's plug that in here for this guy. So I'm going to get equal 1 over eta XJ minus XJ plus 1 transpose XJ minus X star. Okay, and now let's use this little guy right here because I have an inner product between two things that I would like to break apart into some terms that sum, right? So that's equal to, by this thing here, let's move the 2 over there. I get 1 over 2 eta, and then I'm going to get 3 norms. Xj minus, so to get this norm squared, then plus the second norm squared, xj minus xj plus 1 squared, and then minus the difference between the two. That'll make the xj go away, and also I'll get xj plus 1 minus xj plus 1 gone away, minus x star squared. All right, we're nearly done. Because you start to recognize something which is the key step in almost all these proofs, which is that I'm going to be able to take this term and put it together with this term. Okay, I've got plus one of these guys, and this is the same exact term, but just j has been shifted by 1. So if I add them up, it's going to telescope. That means all the pieces are going to go away except the one in the top and the bottom, and I'm basically done at that point. So this is kind of the key: is get something that telescopes. Pick the sum, make it telescope, and then clean up the pieces. And to get to the telescopian sum, you had to do something like one of these kind of things. Okay, the style of these proofs. Okay. Where was I? This comes out of Nesterov's book, by the way, but you can find it a zillion other places. Minus xj plus 1 minus x star squared. So I've grouped those two together, and then out here I'm going to use this other last term, this guy right here. This, again, is my difference in the iterated j plus 1 and j, so that's equal to gj times eta, by my gradient descent equation. Okay, so I'll just put that in here. It's eta over 2 times the norm of g at j. All right. Now I'm going to hit both sides with the summation sign. So I sum over j, and I get on the left-hand side sum over j equals k. Let's go ahead and divide by this as well. Because I divided by that, that operator there will not affect x star. I can just leave it outside the sum. And then I have less than or equal to. All right, so what happens here when I sum this over j? Well, it's a telescoping sum. So I will get x1 minus x star. That will still survive. All right, then when I get x minus x2, that'll get killed off at the next x2, so on and so forth, up to the very top. The top one will be whatever j got up to. I guess it'll go up to k, so I'll get k plus 1 minus x star. Right? I don't have any control over that, but it's a negative sign there. So if I just drop it, I'll get an upper bound. All right? So long story short, after this telescopes, I only have x1 minus x star that survives. Okay? All right? Well, that is within my ball of size r. Okay, so I get r squared. Okay, and so you can kind of see some weakening here. You just need to have the thing be a ball around the initial point x1, not a ball around the entire space, so on. So anyway, I get r squared over 2 eta, and then I divided both sides by k, so I get k there. And I get, actually, no, I don't get the k here because I summed both sides over k. So then I get eta over 2k. And now this guy right here, as I assumed earlier, is that all the subgradients are upper bounded by L. It's our Lipschitz constant. So I'm going to get an L squared there. All right, as you can see, I am basically done. It's now just going to be arithmetic. So first of all, this is not quite in the form of the theorem. We had an F outside the sum. All right, but that's Jensen's inequality, the other super important inequality to know about. Okay, so F of a average is less than or equal to the average of the S. Okay, so just write that first before we talk. So F of the average of xj is less than or equal to, by Jensen, thing I just wrote up here, minus f star as well, is less than or equal to this, which is less than or equal to r squared over 2 eta plus eta over 2k L squared. Yeah? Sorry? On this side here, should be here, 1 over k? Okay. Oh, right. Okay, thank you. Okay, so I'm not going to finish up the last little algebra. We've got on the left-hand side exactly what we wanted. And on the right-hand side, we have something which is now a function of eta. And eta appears in this trade-off kind of way. In one place upstairs, one place downstairs. So there's going to be an optimum choice of eta. So if I just use calculus and take derivative of that with respect to eta and set to 0, I will solve for eta. And what is eta? It's RL. So take dd eta, set it to 0, I will get R over L times square root of K. I will plug that back in. These two terms will become exactly the same as you expect when there's a trade-off. You'll add them up, the 2's will go away, and I'll get the answer. RL over square root of K. Any questions about that elementary simple proof? Okay, so it's a good exercise. You should be really fluent at this. This is like doing your scales on the piano. You should be able to just get out and rip through this kind of. I can't quite yet. I could probably have done it, but in front of a crowd, I decided not to. But it is elementary. But that means you've got to get really. Your brain's got to have it just be ready for you. Okay. So Nesterov's book is a good place to see these kind of proofs. And so I'm going to write down some more theorems without the proofs, but the proofs are kind of in this style. At some point, you need more and more tricks that you get better and better. Just like a musician gets good at doing all kinds of scales, eventually you get good at all kinds of other tricks that you need to do these things. But they're all sort of this style, a page of, Hoshi Schwartz and Jensen and this occasional trick and so on and so forth. Okay? So also Sebastian Bubeck has a nice monograph that's kind of distills some of the material out of Nesterov's book. It's another good source for this thing. So let's start adding some more structure. That was for arbitrary convex functions, no smoothness, no nothing, all right? No strong convexity. So what if we add smoothness? What does smoothness mean? Well, there's many different ways to write it. One way of thinking about it is just Lipschitz for the gradient. So there's the gradient difference that's less than or equal to some beta times x minus y. That's just Lipschitz for the gradient. Let's define that to be smoothness. And here the rate becomes 1 over, not square root of k anymore, but you get a boost because of the smoothness. Okay, so that little lich has gone out of the function. All right, and that's important because as you start to arrive at that little discontinuity, you don't know it's coming. You're kind of going down this nice linear function. At some point, you're going to arrive at it, or you're going to hop to the other side. Suddenly, the gradient has changed sign. Okay, so bang, you get a huge oscillation as you go back and forth across this thing. You now have to try to damp that out. You can't damp that out very effectively, which is gradient descent, so that hurts you. So smoothness gets rid of that and gets you down to 1 over k. What about strong convexity? Okay, so now we're not allowing functions like here. Before we were allowing functions like that. We don't allow those anymore, but we may have something smooth here, but still linear. That's no longer allowed. Now we want something really quadratic-like. Right, so I won't write it down, but that just means that the f of x minus f of y is lower bounded by the linear part plus a quadratic that has a coefficient alpha. Okay, that's strong convexity, and how the rate goes or stays at 1 over t. So rate is 1 over k. Okay, so those are two cases. And what if you now put the two together? Smoothness plus strong convexity. Okay, and now suddenly you go up to this so-called linear rate, which is e to the minus t over q, where q is the condition number. It's the ratio of the smoothness parameter to the strong convexity parameter. Yeah. All right, so a big jump here. And what's kind of happened is that these are now strong enough assumptions where you can make constant amount of progress in every step. You're not kind of getting beat down. You're not making diminishing progress as you go. You're getting a constant progress, so you keep knocking off the error, and that's what gives you this fast rate. All right? For lots of our kind of problems, however, this is starting to get to be suspiciously too strong of an assumption. This part right here is often too strong. All right, what else did I want to say? Okay, so literature's full of kind of things like this. Now maybe do it with the constrained case. You can get into projection methods. They kind of roughly have the same rates in this world. There's also the Frank-Wolf algorithm, which is another way of doing it that you don't have to project, but also achieves the same rates. Okay, so the whole literature doing those kind of things in the constrained case. And then there's just huge numbers of generalizations. What if I allow myself a Hessian and so on and so forth? What if I do stochastic and so on? So this is kind of the language of this field. All right, so the literature didn't quite emerge quite like that. People had analyzed kind of classical algorithms, but these kind of styles of analyses for convex problems weren't really prized. And they became prized when this book came out, Nesterov and Newton, in the 80s on lower bounds. Right? So they said, well, are these the best you can do, or are they just, all this is just one specific algorithm, gradient descent? Is gradient descent the best you can do? Well, clearly not. If I was a super oracle, I could kind of just look up the function in some way and, some arbitrary computation, I could pop to the answer. So I got to constrain my oracle. So they said, well, here's one way of constraining the oracle. Just let it look at gradients. Okay, that's already a little too strong. You could look at gradients in sort of smart places. So look at gradients that are only in the linear span of all the previous gradients you've seen. Okay, so that's what gradient descent does. Conjugate gradient does that too. And you sort of imagine that's already not a bad oracle. Okay, it's not super intelligent, but it's pretty intelligent. Okay, but now let it be an arbitrary algorithm that uses those gradients in arbitrary ways. All right, and you can ask, okay, what's the best I can do within that family of algorithms? Okay, all right. So let's in particular ask, what's the best I can do in that family of algorithms for smooth problems where we were getting rate 1 over k? All right. So maybe naive intuition suggests that you could do the best you can do is gradient descent in this setting, because gradient descent is the locally optimal direction. It's going downhill steepest, right? And we're giving ourselves the optimal step size here. So how can you beat that? And so it was a bit of a surprise to people, I think, and it was kind of revolutionary, changed field, that the best you can do was not 1 over k, it was 1 over k squared. So that's the lower bound for that problem, 1 over k squared. All right. So there was a gap of time in which it was not known whether there existed an algorithm that went at rate 1 over k squared, or there was just this gap, right? And so there was an algorithm discovered, and it's called Nesterov Acceleration by Nesterov, that goes at rate 1 over k squared. And I'm going to write it down here on when I start my slides up. And so he wrote down this algorithm, and no one kind of really understood it. It was just it's not that complicated, but it's just sort of hard. Why that? Where did that come from? And if you listen to Nesterov explain it, he sort of says, well, you're kind of modeling the function. There's not a real it's sort of hard to understand what that means. And so people have subsequently said, well, can I look at other problems, not just smooth convex functions, and get also a lower bound, and then see if I can achieve it with something like acceleration? And that happened again and again. And so it started to emerge a whole technology of accelerating classical methods. And the way people were doing it was just kind of algebraically mimicking what Nesterov was doing. And the proofs got kind of very complicated and very elaborate. There's a kind of a technique called estimating sequences or estimate sequences that Nesterov developed, which kind of helps you a little bit. It has kind of a Lyapunov flavor, but it's also kind of hard to understand. Okay? So I'm going to argue here that this is all very interesting and fundamental, and the only way to understand this really is to go to continuous time. So all this work was being done in discrete time, and acceleration is a mystery in discrete time. But in continuous time, it's not such a mystery. All right, so that's my historical and kind of, a few concepts kind of background to get us all motivated. Does everybody feel comfortable with where we are now? Okay, are you interested in learning about accelerated methods? Okay. Okay, maybe one other thing was important historically was something called mirror descent. Does everyone know what that is? So mirror descent is really the long story, which I haven't decided what I'm going to talk about tomorrow, so I could just decide to do some of that. But roughly speaking, mirror descent kind of comes from the observation that gradient descent can be thought of in a more variational style. And instead of just follow the gradient, you say, well, given where I am now, I'm going to pay a penalty to move further away from that. I'm going to trade that penalty off against a linear approximation of the function. Frank Wolff has his flavor too and all. So this is kind of another way of thinking about gradient descent. All right, now if I make that penalty function literally a quadratic ball, I get gradient descent. But if I make that penalty function something else, like Hale divergence, right, then I get another algorithm. Right? Now in Euclidean spaces, you don't get any advantages by doing this. You're just back to gradient descent. Right? But in non-Euclidean spaces, or things like where the norm is the L1 norm, okay, then you can actually get major improvements here. So you can get algorithms that don't pay a cost linear in the number in dimension. Okay? So you can get dimension-free kind of results there. So we will talk, I think, at some point, at least a little bit about mirror descent. But it's kind of another level of sophistication in these ideas. It's not a competitor to gradient descent. It's just a kind of extension of it. And the best way to think about it is that when you go to Banach spaces, where you're not in the same space with the primal and the dual, you have these two separate spaces. That's kind of how mirror descent is always set up. All right, so I'm going to now go to my slides. If I can get back up. All right, can I get some help on? Excellent. All right, so these are slides that were done about a month or two ago for a particular purpose, and I've added to them a little bit for today's talk. Let me acknowledge my collaborators here. These are people, Andre Wibasona and Aisha Wilson are students with me at Berkeley. They've both done really, really very important parts of this work, ongoing in both cases. Andre has moved on to Wisconsin, and Aisha is still with Berkeley. And then the last little part on symplectic integrators, when I started thinking about that, I was giving a talk at Stanford, and I mentioned symplectic integration. And Mike Betancourt was in the audience. He came up afterwards and introduced himself and said, you know, I know a lot about symplectic integrators. You know, we talked some more about it. So I had him come up to Berkeley. We started talking and started working together. And so he's contributing at this point on that part of the project, which you'll see near the end. Okay, so let's, first of all, a little bit of philosophy. You know, one of my favorite theorems in the world is something called the fundamental theorem of calculus. I've always found it fascinating how you can go back and forth between integration and differentiation, right? And I also am fascinated by, I was fascinated at some point by Lagrangian mechanics. If you've ever studied it, you know, it's this kind of wonderful moment where you see that Newton's approach to mechanics can be done in a different way. So Newton's approach to mechanics is based on differential equations. You know, F equals ma is a differential equation. You can write it down, and then that defines sort of paths by integration. Okay? Another way to do that is to don't go through differential equations at all, but start with an integration procedure. So you write down the integral of a energy, okay, and you find the path that minimizes that. That's the Lagrangian approach, and classical mechanics can be done in one way or the other. So one way is kind of integration-based, and the other way is differentiation or differential equation based. Right? And so we see this in lots of the fields where you can kind of approach things through an integral approach, integral of something that you optimize, or you can approach it directly through derivatives and paths, okay, and dynamics. So the former approach I would call variational. So variational just means that you start with a problem that's defined maybe in terms of differential equation or paths or something algebraic, and you turn it into an optimization. Right? Now, when you turn something into an optimization problem, often that's interesting because now you can perturb the optimization problem. And after you perturb the optimization problem, you can solve the new problem. Maybe it's easier in some sense, and maybe you'll get an answer which is approximately a good answer to the original problem. So that's what, when we talk about variational methods in statistics, machine learning, we typically mean. All right, so I've worked a lot on that, and that's really all that is. It's just a particular way of turning a problem involving cumulative functions, really, into an optimization problem. Cumulative functions an integral, turn that into an optimization problem, and then approximate calculation. If you're talking about eigenvectors or eigenvalues, there's the algebraic way to define an eigenvalue is just AX is equal to lambda X. It's the biggest lambda that solves that equation algebraically. But you can also write the Rayleigh coefficients of the matrix, X transpose AX divided by the norm of X. And find the biggest lambda which optimize that with respect to lambda. Okay, sorry, with respect to X. That gives you a variational characterization of eigenvalues. Okay, so the most mature fields tend to kind of have a real strong interplay between differentiation and integration, going back and forth all the time. You know, so in physics, certainly Lagrange kind of initiated this, and then Hamiltonian approaches. You will see also Laplace expansions is kind of a way to take an integral, turn it into an optimization problem, and saddle point expansions more generally are ways to do this. Those technologies started in physics really, but they were brought over very quickly in statistics. In fact, Laplace kind of was bridging statistics and physics while doing that work. You know, that was kind of an era, quite exciting era in the early 1800s. In fact, Lagrange, by the way, is I like to mention, is even despite the French name, is an Italian. He grew up in Turin, and his real name was Giuseppe Lagrangia. So I'm married to I'm an Italian citizen, so I'm kind of proud of Lagrangia started. So anyway, those fields are quite mature, and they have a blend of these ways of thinking. Optimization, not so clear. Okay, I guess I should say one of the numerical disciplines. If you look at finite element analysis, kind of the key to doing civil engineering, finite element analysis is exactly a variational approach to the partial differential equation of mechanics. And then Monte Carlo is really a blend of optimization and integration. Basically trying to solve an integral problem, but you often will take derivatives to get you to flow with long paths. So anyway, optimization, this historically very deep field, is still in some sense immature in this way, that you will pick up optimization papers and they're full of derivatives and Hessians and et cetera, covariance, differential geometry ideas. And you'll almost never see an integral sign. Okay? The only place you'll maybe see it is in a Taylor expansion of the stuff that you're ignoring. Okay, so let's repair that. Let's start to bring a variational approach into the optimization field. So let's stay with convex optimization. I actually am to do some non-convex things later here, but probably not today. And we've been talking about gradient descent. So here I've written it again, and we've learned that it has a convergence rate of 1 over k. I guess this isn't a smooth case. I didn't know that. Okay, so finally you now get to see Nesterov acceleration. So as I alluded to, people at some point realized this was not an optimal algorithm, kind of surprisingly, and is there an optimal one Nesterov discovered? So here it is, accelerated gradient descent. It now has not just an x value, but it also has a second sequence, y. The y sequence takes the gradient descent in the x space, right, and takes a step, right? And then x is a convex combination of the last two values of y. Okay? So some people find that not at all mysterious. It just seems natural in some ways. Others find it mysterious. It looks kind of, there's something called the heavy ball method. It has kind of a momentum interpretation, and there's many kind of intuitions here, but none of them kind of immediately lead to that equation, right? And they don't generalize typically. I'm going to show you some of the results here in a minute. Right? In particular, this equation here is this convex combination, is natural in some sense, but it's not dynamically, it's a rotation. Okay? So it's kind of dynamically kind of weird that you would rotate. Right? Moreover, this pair of equations it's not a descent method. So it will go down for a while, then it'll go back up. Then it'll go down, go back up. So that seems suboptimal, but it's actually quite the opposite. It's optimal. Okay, so you can analyze this using this kind of math, but a little bit harder, sort of 3 pages of stuff. At some point becomes kind of mysterious, and out at the end pops this rate. So subsequently, that was in 1983, and it's amazing how few people know about it. Just this kind of cadre of people in optimization tend to know about it. But then at that point, people start looking at all kinds of other procedures, mirror descent, cubic regularized Newton, et cetera, et cetera, et cetera. I listed only those. These are well understood. They're descent methods and so on, but people realize that you could accelerate every one of them. So there's now accelerations of all those things. They're very important for theory, and they're also important in practice. So FISTA is something that people use a lot in practice. It's where you take a optimization problem and break it into 2 pieces. And you have an F plus a G. And we have that very commonly in learning problems, and so that style of work is important. So anyway, they're still mysterious. There's this analysis style, which is this thing that Nesterov cooked up called estimate sequences. They kind of have a momentum flavor, but that's kind of really only true in the Euclidean case. So there has been a slew of papers trying to give some explanations to these things, and these are beautiful papers. So Chebyshev polynomials are something you do in numerical analysis, and Moritz Hart kind of tied that there. That's only for you for the quadratic case, however. Okay, so beyond that, it's not very high. I also like this geometric shrinking idea, and so on and so forth. So these are but they're only for strongly convex functions or first order methods or Euclidean or quadratic. So it's still kind of not clear what the underlying mechanism is. Okay. All right, so I'm going to argue that it's kind of the problem is that we're trying to talk about acceleration, and we're talking in a class of algorithms that hop around. And it's kind of just not clear what you mean to accelerate when you're hopping around. Acceleration is when you push on the pedal, the gas pedal. Okay, so let's in fact go into continuous time and see if we can make progress thinking about it there. Okay, so there is a huge field called gradient flow. If you don't know about that, it's often actually Europeans who work on it. D'Ambrosio in Italy is a leader in this. So gradient flow is just a differential equation where you take the gradient and you move along that direction. There's no step size. It's just a differential equation. If you take Euler approximation to it, an Euler step, the current plus thing plus the gradient. That's a discretization of that differential equation. That gives you gradient descent. That's one way of thinking about gradient descent. Okay? You can analyze the convergence rate of this in the same kind of way we did before. Okay? And you get a convergence rate, which is, not surprisingly, 1 over t in the smooth case. Okay? Okay, so that was a nice paper by Suboid and Candiz in 2014, where they said, well, can we take the Nesterov equation and take the step size to 0 and see what differential equation we get out? Okay, so they did, and you can do it yourself. I wrote the equations down. Just take that to 0, and out pops a little second order differential equation. X double dot plus 3 over t, x dot plus the gradient. Okay, so first of all, that was interesting. They analyze this a little bit. You can't solve it, but you can use Bessel functions to approximate it, and you can start to understand a little bit about the oscillations that you get here. As I said, it's not a descent method. It oscillates, so you can start to get a little insight into that. But it's still a mystery. Where does this differential equation come from? Does it have any? Why is it achieving the Oracle lower bound? Why is it optimal in any sense? What's that 3 sitting in? Why is that? Why is there a 3? Et cetera, et cetera. Okay. Okay. Nonetheless, it's progress, and when we saw this, we thought, well, okay, there must be an underlying generative principle that is delivering that differential equation, and probably deliver some other different equations. Can we find that underlying generative principle? Okay. And what we're doing when we're posing that question is we're saying, is there an optimal way to optimize? Because we're trying to get these Oracle lower bounds, which is the best. Okay. And what we're asking is there a kind of a generative principle for doing that, for achieving these bounds? Is there an optimal way to optimize? And that somehow is what the field should be after, right? Optimization shouldn't be, here's a list of methods, and they have these properties. Okay. It should be that of all those methods, there's got to be some best methods. And can we have a way of expressing that mathematically? Okay, so I'm going to claim we're going to provide that here. Bernard, how much time do I have left so I can calibrate a little bit? Okay. Okay, so we're going to do a variational approach to this. Okay, so instead of working with differential equations, we're going to do just what Lagrange did, and we're going to go to a integral of something and optimize over paths. And we're going to try to figure out what the optimal paths are for optimization. And then, in fact, the acceleration is just going to be our speed of movement along the paths. The whole problem is to find the path, right? Not the speed. Okay, so on the next slide, I'm going to give you the answer. Here, after quite a bit of work, we discovered this object right here. So this object we're going to call a Bregman-Lagrangian. Maybe I'll go ahead and show you what Bregman divergence is if you already know. So the first term there, so there's a bunch of alphas and betas and gammas. Those are going to not be very important. Those are just degrees of freedom, time scaling functions that give us a range, a space of algorithms. It's not the core part. The core part is the f that's sitting there and also this thing dh. So dh is a Bregman divergence. Hopefully you know what a Bregman divergence is. It's a way of measuring distance in general spaces. So if I want to measure the distance between x and y, I throw down an auxiliary function h, take the linear approximation to h at x, roll that out, and find the discrepancy between that prediction and h at y. And that vertical red distance there is the distance between x and y. So the vertical distance becomes a horizontal distance between x and y, called the Bregman divergence. If h is quadratic, this just delivers back the Euclidean distance between x and y. It's just a variational way of writing Euclidean distance. Right? But if h is something like Kolbeck-Leibler divergence, then you get out something different. Get out if h is a logarithm, then you get out Kolbeck-Leibler divergence, and you can get other kind of divergences out from this formula. Okay. So anyway, we are using the Bregman divergence, and then h is a degree of freedom of the algorithm. The user would get to choose h, depending on what kind of algorithm they have in mind. But the key is how we're using the Bregman divergence. So we're measuring the Bregman divergence between x, where you currently are, and x plus a time scaling, e to minus alpha t, times x dot. So it's a little bit like you're kind of looking ahead in a certain direction, given by the flow, and you're sort of asking about how, energetically unfavorable or favorable that is, measured in terms of Bregman. Right? So you're going to trade that off against the desire to go downhill, because f is trying to go downhill. Okay? So that has a little bit of flavor of a Lagrangian from physics. And in fact, if you set h to be the quadratic, the special case of quadratic, then then this just simplifies to 1/2 x dot squared. That look-ahead Bregman divergence. So that's literally a kinetic energy, and this is literally a kind of classical Lagrangian, where F is now playing the role as the potential energy. Okay, what about these alphas, betas, and gammas? Well, again, those are just degrees of freedom of space we're working in. But it turns out to achieve, with this formalism, the optimal rates, we could achieve slow algorithms, but we want to get these fast algorithms in this space, that there's only 1 degree of freedom, just alpha. So given alpha, you need to set beta according to this differential inequality, and you need to set gamma here, and so that pins those down, okay? So we call those the ideal scaling equations. They're going to give us the optimal rates. I'll show that here. Okay, so what do you do with Lagrangians? Well, this is just a reminder of the calculus of variations. There's the Lagrangian again at the top. I'll start getting out this thing. And what do you do with Lagrangians? Well, you put them inside of an integral sign. You integrate, and then you find the minimal path, x, the whole path, that minimizes that thing, which is sometimes called the action. All right? So that's a problem in the calculus of variations. And if you've studied that, you will know about the Euler-Lagrange equations are necessary and sometimes sufficient conditions for finding the optimal paths. It's like setting all the partial derivatives equal to 0 in classical vector spaces. It's the extension of that to the continuum. So instead of setting all the partial derivatives equal to 0, you take a bunch of partial derivatives here of L with respect to the 2 arguments, x and x dot. You take a total time derivative, and these things have to give equality. That's a necessary condition for optimality. And this is very easy to do. You can just take that L, plug it in here. I can easily take the derivative with respect to x and with respect to x dot, and then I can take a time derivative, and out will come a differential equation. So here is that differential equation. It's a nice little exercise for you. Here it is. So let's call this the master differential equation for acceleration. I claim that this will deliver the Suboid-Candice thing, and therefore Nesterov acceleration in classical gradient setting, but it will deliver essentially all known acceleration algorithms in continuous time. Right? I'm going to explain. So let's look at it. It has a second order term here. It has some time scaling. Then it's got some damping. And then here's a bunch of stuff which we'll just call geometry. Okay? Then the geometry rescales the gradient. Okay, so have we learned anything at all from getting a differential equation? Well, let's go back to some of our tasks. First of all, can we get a rate? And we're trying to show these are optimal rates, but we actually just even get the rate at all. And so for the classical algorithms, the rate was the kind of analysis I did here. And as I alluded to, if you go to other problem settings, you have to do similar algebra, but often with a whole lot more work and more tricks are needed. Okay? So the first amazing thing that happens here is that we're going to be able to get a rate for this differential equation with one-line proof, all cases. Okay? And so here it is. So the rate is that discrepancy goes as e to the minus beta t, where as the designer of the algorithm I chose beta. And here's the proof. You write down a Lyapunov function for this dynamics. The Lyapunov function depends on the Bregman divergence in sort of a rearranged way. Okay? So we just designed this thing, and then we take the first time derivative with that. And by the Lyapunov theory, we need that to be the time derivative be negative for convergence. Right? And that is achieved if and only if I have this rate here. So it's a one-line proof for these rates, and there it sits. Okay, so that's interesting. Looks sort of suggested when we found this that we were on the right track here. We're getting something out of this math. But first of all, it's kind of weird that it's e to the minus beta t. That suggests we're getting exponential rates in general. We know we can't get that. We expect 1 over t squared, and maybe occasionally exponential. That suggests exponential. Well, all that means is that, first of all, we can achieve exponential rates in continuous time. It's not going to be that hard. But also, we don't necessarily expect for all problems to be able to set beta just to, something like, t. So we're going to have to set beta to logarithm to be able to get logarithm of t, to be able to get actual algorithms for particular problems. And what's going to break, actually, if you go into a problem domain and you try to set beta too aggressive so that you get, say, an exponential rate, but the differential equation will not break. It'll still work. You can do that in continuous time. What will break is actually the discretization of the differential equation. It will not be possible to discretize it stably. Right? So there, we're suggesting we're getting into this kind of area of geometry called symplectic geometry, which is getting a little bit of depth mathematics. Okay, so let's just, first of all, not be ambitious. Let's don't try to get exponential rates and all. Let's just try to do what we know we can get. Let's set beta to be logarithm of t. So when I take e to the minus that, I get 1 over t. Okay, and in fact, let's get ourselves an extra free parameter here, get a broader class of algorithms. Let's set that if it's 1, I get 1 over t. If it's 2, I get 1 over t squared. Maybe I could even get 1 over t cubed and 1 over t fourth. Maybe I can get a whole bunch of polynomial rate algorithms. Okay, so let's make that, let's say that's a possibility. So setting that in that way, that determines alpha and gamma, so I'm kind of done. All right? So now, if I plug beta t in here, I get a rate which is 1 over t to the p, includes 1 over t squared, and so on. And if I plug these into that master equation, here's the new differential equation that pops out. So first of all, it starts a little simpler. I do get a 1 over t here as my damping. And the case where p is equal to 2, all right, where I know I'm getting that Nesterov rate of 1 over t squared, actually gives me a 3 here. So the mysterious 3 is kind of a coming out, right? And if this is Euclidean here, this is just quadratic, a lot of cancellations will happen, and all this stuff will vanish. And we'll get back to that very simple supercandescent thing. Yeah, I saw the hand back there. I just wanted to get to that. So for the supercandescent, this differential equation just comes out as a special case of this when h is quadratic and p is equal to 2. And there's also one other paper really in this field, Krichin et al. had done the same thing for mirror descent, not the Euclidean case. And they also got this 1 over t squared, and we would cover their differential equation. Yeah.
Okay. So this choice of beta t, I think I missed your point. Like, does this depend on f at all, like in the smoothness?
No. So f is in some class of functions. All right. So I know that. I'm giving you the problem, and you're saying, well, I'm trying to design an algorithm to go down to Helmholtz class of functions. Okay. You can now choose beta t in your way, right? And if you choose kind of a dumb beta t that's too slow, you'll get an algorithm which converges and all. It's just not a good algorithm. It's not as good as it could be, right? And you could say, okay, I learned that I can turn beta t up. But you can turn beta t up to some point beyond which you can still, your algorithm still works at continuous time, right? But in discrete time, you can no longer discretize that different equation. It will not be stable, right? So it is in some sense determined by not just by a specific f, but by a class of f's, right? But it's in some sense math is needed to figure out what that breaking point is.
So here, do you have any characterization on what type of beta do you need for what classes of f?
Yeah, that's going to be. Okay, so far so good. Okay, so there's still a lot of mystery here. So we can recover some known differential equations, and we can get our general rate. That's the progress so far. So in some ways, not that deep. Okay, so now let's look at different values of p and write down the differential equations for p equals, say, 2 and p equals 3. All right, so I've done that here. P is equal to 2 is that differential equation, which I just had on the previous page. And then p equals 3, here's the new differential equation. And its rate is 1 over t cubed. Okay, and in fact, this differential equation does have that rate. We've achieved this rate in continuous time. Right, no big deal. Just that's our general theorem about rates. Okay, now if you look at this differential equation, this one, you don't have to be an expert in differential equations to see they're pretty similar. Okay, it's basically the same differential equation. That 3 is changed to a 4, that 4 to a 9, that 2 to a 3. Okay, all right. So in fact, all that's happened to go from here to here is that we have chosen a different clock. All right, so if Bernard is using a clock that measures in some units, t, I can choose different units. I can use t to the 3/2 as my definition of a clock. All right, perfectly fine. I can do that. And when I reparameterize time in that way, I go from this differential equation to this one. Okay, so his differential equation and mine really are the same. I'm just using a different notion of time. So it's just Einstein, if you will. Different clocks, but they're all the same. Right? And if someone out in the audience says, well, I had a different clock that goes at t to the 5/2, fine, you can do it. And what's happening is that we're all moving along exactly the same path. Right? If, as I chose in different values of p, I'd get in different paths, then this formalism wouldn't be that interesting. It's just a way of describing the different paths you get off for different problems. Right? But it's turning out that we're getting the same path for all problems in this big family. Right? Right? That's interesting. We have discovered in some sense an optimal way to optimize. It's that path. Right? And the notion of acceleration on that path is actually uninteresting. You can turn up the clock speed. You can use whatever clock you want. You can have an exponential. His clock could be t. Mine can be e to t. I can look like I'm moving super fast. Well, I'm going along the same path. Okay? So it's not interesting in continuous time at some level, right? But as I did that, if I zip along that path at some e to the t rate, okay, I will get a differential equation, which are, not looking quite like that, right? And I can say, well, I got to put this on the computer. I can't solve these things. There's no analytical solution. I got to put it on the computer, discretized. I will not be able to discover the discretization allows me to put it on a computer. There, my greediness hurt. Okay, so it's breaking. All right, now what's the proof that that for all values of t we're getting the same path? Well, it's a bit of differential geometry. It's that this operator, this Bregman-Lagrangian, is a covariant operator. So if you know that language, it's a covariant operator, and that the proof of that is extremely simple. Is if I just reparameterize time, and I write down the Bregman-Lagrangian for the new parameters, then all that happens is the parameters just change by a little, a one-to-one transformation, right? So that's I stay in the same path. Okay, so hopefully now you found that interesting. There is an optimal way to optimize. It's characterized by a Bregman-Lagrangian, and so in continuous time we've kind of discovered something, right? But we got to go back on the computer and eventually get algorithms that people can really use, right? So what must be happening, as I've been alluding to, is that something's breaking the discretization, right? Now, so at least my first thought when we started understanding this was, oh, maybe this is not very interesting. This is just the numerical analysis part of it. But that's not the right way to think. The numerical analysis part is the whole part of the story. That's the important part of the story, right? And so at that point, I actually remembered that I'd taken a class back at MIT because I was just interested in learning more math, and there was a class on differential geometry where people mentioned symplectic integrators, and it stuck with me a little bit. And basically, all I remembered was, roughly speaking, this is a particularly nice way to discretize certain classes of differential equations. It was discovered by Hamilton and Jacobi and others. Jacobi. I noticed there was some trucks outside with Jacobi's name on it. Guess he had also a cleaning service. So it's a particular way to discretize certain classes of differential equations. So that was already part of it. And then secondly, to design symplectic integrators. So when you integrate, you typically start at a point xt, and you look at maybe some local gradient or Hessian or something like that. You evaluate those at that point, and then you take a step. That's the explicit form of an update. Another way of doing it is that you're at a particular point xt, you envisage a step, and you evaluate the gradient Hessian out at the end of the step. Right? And you now write down a little equation reflecting that. Right? Now, you have to solve that equation. You have to invert it, effectively, to figure out actually what step to make. That's called the implicit approach to discretizing. Okay? Classically, implicit or explicit, there's a debate about, but they're basically the same. Okay? One's more complicated, you get some advantages and all that. The key is that if you put the two together, you have an explicit and an implicit step together, you get magical properties happen. Those were symplectic integrators are, not all of this form, but that's kind of the general form. And if you've heard about a leapfrog integrator in Hamilton Monte Carlo, Hamilton Monte Carlo, by the way, is the way to do Monte Carlo these days. That's kind of discovered at the largest scale. It just is way better than anything else out there. It's using a symplectic integrator as a inner loop. Okay, so that's going to be the whole story here, is what is symplectic integrators and how does it relate to acceleration. Before I get there, let me just sort of say this. A year ago, we wrote a paper on this, and we didn't know that symplectic integration path would be useful. So we just started trying to discretize these things in kind of a naive way. Okay, so the first thing to do is just to try to, so you have a second order differential equation. You can write it, standard thing to do is to write it as two first order equations, and you can discretize those two equations and see what happens. These slides at this point are going to be lots of symbols that I don't want to get into the details and introduce. It's just when you start discretizing different equations, you get a bunch of symbols. It's not particularly interesting. Just follow what I say, and if you're confused, stop and I'll try to explain, but by focusing on all the symbols, it will not help. Anyway, you can write that second order thing as two first orders. There they are. And you can discretize those two things using Euler discretization. And you get out this pair of equations. It's kind of been, I've brought it together in a clean way, kind of looking like a prox method. So you get a step in an x variable, and you get a step in a z variable. It's written as an optimization. And there is your discretization. Okay, so you could put that on the computer, and we did. So you put it on the computer, and here's a quadratic function. It converges, and it kind of hovers around there, and then it shoots off to infinity. Same thing here. Goes down, looks like it's doing very, very well, and it shoots off to infinity. Okay? So you would never want to put this on a computer, or at least on a real-life application. It's not stable. All right, so we thought, okay, runga kata, or maybe stiff differential equation technology. What do you do with fluid? So on and so forth. So sort of going through those things and realizing that none of them were stable. All right, so we thought, are we stuck? Is there no way to discretize this differential equation? Well, it has to be, because we know that Nesterov acceleration is a set of discrete equations, and some would say it's related to this. We've kind of showed that they're close. So at that point, we went back to Nesterov style thinking, but from a new point of view, which is thinking about as a way to discretize differential equations, right? So here again, I don't want you to pay too much attention to details, but here was the two equations we had before, where this was a z variable and this was an x variable. We've now introduced a third sequence, y, plugged it in here and plugged it in here, okay? And we'll write down an equation for y. We'll now get three sequences. And if you're in this area, you know this is kind of Nesterov style. What you ask is that this gradient here, when you inner product with the difference between the x and y's, that it is bounded below by something which involves the dual norm of the gradient. Okay, so this is a famous equation. It's achieved by a variety of methods, in particular the primal methods achieve this. So we know how to achieve this. And what we were able to show, not that hard, was that if you achieve this, then this pair of equations actually is stable. And moreover, it has the fast Nesterov rate. Okay, so we're using Nesterov style thinking as a way to design a discretization here. And having designed it, we were able to prove a theorem that our convergence rate is in fact 1 over k to the p, the fast rate, 1 over k squared in the case p equals 2, and so on. And in doing so, we've actually now proved that we can get fast rates of order 1 over k to any power, k to the 4th, k to the 5th. We can do any of those, right? So that's a novel result. Okay, so there's our convergence rate, and to actually then achieve this sufficient condition, again, it's known how to do it. You simply write it here as a Prox method. This is a primal algorithm here, and classical results to Nesterov and others show that it achieves that sufficient condition on the previous page. So this triple of equations then provably has this rate, and it's stable. You can put it on the computer. Okay? So at that point, we did a bunch of experiments. We published, wrote a paper, and everything. In some sense, we're kind of done, but not feeling very comfortable with, well, we got this beautiful object, Bregman-Lagrangian, but we didn't know how to discretize it. We just hacked around until we found a way to discretize. Okay, so at that point, I was kind of going around a few talks about it, and I was mentioning, hey, I remember symplectic integrators. I bet it has something to do with this, and we started thinking about that a little bit more. Let me just summarize before I talk about symplectic integration a little bit, what we've done so far. So here is kind of where the literature has been. With gradient methods, we've all loved gradient methods, including stochastic gradient. They have slow rates, however. 1 over k to the p minus 1. Okay? It's been known for a long time that you can go into the continuous domain and write these things as gradient flows and discretize them. In fact, you can also do this for higher order p, where you divide by the dual norm of the gradient in that way. And you can get these slow rates in continuous time and analyze them as well. Full literature is a huge literature on that. What Nesterov showed us how to do was to break through this barrier and go to the right-hand side here. In discrete time, he showed us how to achieve the fast rate of 1 over k to the p. And what we've done here is add, let p be bigger than, in fact, Nesterov had a paper where p was equal to 3. So we've been showing it beyond. Okay? So that's the Nesterov rates. And what we've done is to add this thing up here. Is that we say, well, you can move this class of methods into continuous time, and the right way to express that is with an Euler-Lagrange equation or a Bregman-Lagrangian, and you can easily see that you get a fast rate in continuous time. Okay? So this kind of diagram now starts us kind of on a path of many, there's many other explorations. You can do this stochastic, you can do this on different manifolds. There's a lot to do. This is just a very first start of this little, I hope will be a big literature. Moreover, you can now assume other things than just smoothness and convexity. You can assume, say, uniform convexity. It turns out you get exponential rates, all sorts of things you can do. Take this diagram. Okay, so but in my last few minutes, or whatever, let me say something about symplectic integrators. But before I do that, let me just stop and see if the story so far has triggered any questions. Not generally, no. We have explicit control of the constants in these complexity, all these big O's, I'd say in some cases, yeah, they're related to Lipschitz or smoothness or constants, but the methods can deteriorate. Well, so none of these constants are hiding factors of, K or T. None of that, no. Dimension's an issue, but remember, we're kind of just redoing a vast literature here from a new point of view. And so, say, mirror to strength, we know handles dimension very well. And stochastic gradient handles dimension very well, and so on. So we're not needing to reprove the kind of how the constants depend, the dimension dependence appears there. We know that, right? So you're asking if in our papers when we wrote things out, we were careful with that, but mostly not. But as things goes on, we'll have to be careful. But that's not going to, we're not going to lose that kind of favorable property. Yeah.
So you were saying the Lagrange equation is just a so nonlinear transformation of time scale. Just wondering, is there maybe something you can say about that characterize this, that necessarily lead to this class of equations? Ask for general.
Yeah, that's a great. Haven't thought about that. I don't know if that's true. I doubt it's true. We basically has got this particular subfamily of equations that have this nice oracle property, and we're seeing that we get enclosure in that subfamily. So it's a carved out an area. But what's missing, in fact, philosophically very interesting and deep, I intend to think about it, but I don't know, is that you would like to take some axioms that describe the oracle, okay? And start from those axioms and derive the Bregman-Lagrangian, for example, or derive other operators that also achieve oracle. Right? At that point, you might hope to get a characterization. But these oracle model, the Nesterov student oracles are kind of mathematicians' oracles. They're a way to get, a particular existence statement. Okay? You find a worst-case function in there. So it's not really very generative. So what we're kind of missing right now is a kind of a generative way to write down what the oracle does, and then from that derive the Bregman. So I think that I'm not enough of a physicist to really know, but I kind of think that happened in the late 1800s. There was Newton and there was Lagrange, and then about 100 years later, people were able to axiomatize and kind of here's the reason the Lagrangian arises from symmetry principles, gauge, and so on in physics. So that's physics. That's not our field here. So I have hope that that's possible, but it may take 100 years. So, or I don't see it right now. So we're in this space. It's interesting. We're exploring it. It captures lots of no results, but I definitely don't know what's up there. So. Anything else? I'll pause. It's a summer school. You just ask questions. Yeah.
Hi. So in the gradient flow, where I missed out how this rescaling.
You mean the denominator?
Yes.
I never explained that. So that part right there, I just talked about first order gradient flow, but that's absent. It just is the case that if you write down that dual norm and take it to that power, and you discretize with Euler discretization, okay, that you will be delivered an algorithm which is a higher order gradient method. So it can, for example, it can pick a p minus p-1 Taylor expansionary function instead of a linear one, and then it wants to move you a distance which is constrained by the k to the pth norm. Okay, so it's that generalization, right? That is a gradient-based algorithm, and that is the algorithm that's gotten by discretizing this guy right there. So I don't want to spend. D'Ambrosio has his book on gradient flow. Highly recommend if you're interested in these things, you'll read it. You'll find that kind of thing in there. Moreover, you'll find these flows on probability manifold, which is very, very interesting. So I should say we've done all this work so far. In fact, most everything else I would say in this line has been done with differential equations and deterministic gradient descent. What about the stochastic case? Well, in the stochastic case, these objects will become diffusions. They'll become stochastic differential equations, and there should be an optimal way to diffuse. Okay, and there should be a Fokker-Planck equation. Here we're Planck, right? Planck's function. there should be a Fokker-Planck equation for this kind of thing that generates those things as well. When you go to those objects, the gradient flow perspective will also be of interest, kind of what's the stochastic flow here. But that's an open area that we can work on during the next year. Yeah. What happens if you have constraints? Basically, constraints in this world, I hate to sort of say sweeping statements, but constraints don't hurt you in this world, in this general convex world, in the sense of you don't lose the rates. There just needs to be a projection step back on the constraint set at some point, and the projection step is typically a contraction, and just in the sequence of inequalities, you get another inequality due to the projection, and it doesn't hurt you. That said, to do the projection in real life, it may be computationally hard. There may be a little inner loop there, which is hard to get. Frank Wolf is a way to go to gradient-based things that don't require the projection that also have the fast rates, and that's kind of one of the reasons they're favored. I don't know if you've been hearing about those this week, but you said, I don't know about that. That's a great question. Can Frank, does anyone know Frank Wolf, accelerated Frank Wolf? You think it's not done yet? It could be. There's lots of gaps here. And kind of the reason I talked about all this stuff is that as grad students, there's lots of things here, holes to be worked, things that could well be. You take any like a distributed, stochastic, constrained, et cetera, you put together any combination of those, probably there's not yet a paper. And it's probably interesting. So it's a very interesting time in this field. Yeah.
How did you come up with the Bregman-Lagrange, with the Bregman-Lagrangian? Is there some
Yeah, this is just, this is just kind of sitting around the whiteboard and try to reverse engineer what's out there, really. And there's a second paper I should mention, which I don't think I included here, but Aisha Wilson followed up. She has a paper with me and Ben Recht on Lyapunov approaches to this thing, which is related but a little bit different. She's found a general way to write Lyapunov function, not just for the continuous case, which I showed you, but I write a corresponding Lyapunov for discrete, and to go back and forth between those two. So that was kind of very interesting. So now you can start with your Lyapunov function, which you wrote down in continuous. You can then derive a Lyapunov function in discrete and prove convergence in discrete without the kind of machinery, the continuous time machinery. And so in some sense, that replaces the estimate sequence technique with something much more familiar, Lyapunov theory, in discrete time. But again, Lyapunov and these kind of things always you come up with them by reverse engineering what you're hoping to get and tweak things back behind the scenes until you get what you want.
And afterwards, do you have an interpretation of this your Lagrangian, Lagrangian in terms of energy or something like this, or?
No, I mean not physics. I mean it really is just a general energy. It's a Bregman divergence energy. So those kind of energies are used in lots of areas of math and econ. But other than that, it's just a word. Energy is a word in physics because it's conserved. Right? If it weren't conserved, it really probably wouldn't be a word. So I don't know what the relevant conserved quantities are here. So, yeah, great question. Again, that's kind of what Bernard was asking about. Is there or at least my response to Bernard was talking about, is there should be some axioms that kind of here's some quantities you're trying to optimize, and that leads to a expression. Kind of in the middle, sort of jumped in and reverse engineered something. No, there's no more intuition beyond the ones I was trying to give you. That it's kind of a look-ahead operator, and we're very used to working. If you know about mirror descent is basically we do projections in Kullback-Leib and Bregman divergence. Sorry, in Bregman. So we're very used to that. I'd hesitate to give that energy. Yeah.
Hi. Is there something that we can learn about sampling from your results? If we take like a gradient descent and we add some noise on it, we get Langevin diffusion. And is there something that could learn for sampling from that approach?
So as I alluded to, that's pretty much open. It's something that we are working on. I have a couple of students working on it right now, and this fall and spring this coming year we'll come a lot more. I don't want to restrict myself to Langevin diffusions. So basically, the right intuition, and we already do have a paper soon on this, is that these are momentum-based methods. These aren't just gradient flow. Okay? In fact, gradient flow does not give you that covariant problem. We had to go to the momentum, right? Second order differential. When we got to that, we got this covariance, we got this nice thing. And so Langevin is first order, so there needs to be a second order version of Langevin, which I think is like kind of SDEs, not just Langevin. So we have there's a paper will come out which has a convergence result for a certain class of second SDEs. There's no other kind of connection yet. You're absolutely right. That's fantastic, interesting. And I don't know enough about the discretization of SDEs. It's kind of also something I ask my colleagues who work on finance. Do you work with these SDEs all the time? Do you ever work with ones that diffuse but also oscillate? And if so, how do you discretize those? I have no idea. So, if the audience are interested, should get in, dive in. So yeah. No. So certainly the rates depend on it. Yeah. So most of what's being said here doesn't depend on convexity, actually. So really the algorithms can run in the non-convex setting, and they can often do good things. I am going to be talking, probably it looks like tomorrow, I'll be talking about some non-convex things, and I think Supreet also did as well. But so saddle point avoidance is a very interesting problem. One of the first things you can look at when you're looking at a non-convex case, how long do you get stuck near saddle points? Eventually we know we'll get out of it. But if you're stuck too long, then you may have waited and your algorithm you think is converged and you're still next to a saddle. Momentum in some sense, or acceleration, you hope should get you faster out of saddle points. If I'm kind of getting stuck, that momentum will kind of wash me out and kick me out faster. That's not known. Stochastic, having some stochastic is known to help you. And in fact, we have a paper now, if and only if. Without stochastic, you're not going to efficiently get out in dimension, get out of a saddle. So these are, I think, the class of algorithms we're looking at for non-convex, and the analysis style will be very similar. There's going to be a few steps that need to change, and we're not quite sure what we're looking at. Right? Lower bounds there, it's a little harder. So that's also very much. Yep. Yeah. Yeah. No, he's asking about convergence of the function value, not the function values, but the actual iterates. And my sort of take on that is that, so when we go to the non-convex case, we're not going to expect convergence of iterates. So we really want to get just the gradient small, and we want it not to be a saddle. And so getting the gradient small is going to be our general focus. Norm of the gradient should be small. And I think of it as kind of an older literature in optimization where they were mostly worried about the iterates. So one could try to do it anyway. We haven't done it. It's not been the focus. You need some geometric structure to achieve. Okay, how am I doing? I think I sense 5 or 10 minutes. Is that right? Okay, then let me just do this last little bit, which is your pictures, and then we'll be. So that's a summary. Okay. Oops. All right, if you know what a Lagrangian is, if you had some physics background, you probably also know what a Hamiltonian is. So a Hamiltonian in physics you get by taking the kinetic energy plus the potential. That's not the general way to think about it, however. The general way to think about it is to take your variables x and x dot and do a Legendre transform, or a Finchl transform, to turn x dot into another variable, which we could now call the momentum variable, called p. So x dot, you go to x and p. And in those new variables, you rewrite your Lagrangian, and here's what happens in our case. It becomes an object which we call the Bregman Hamiltonian. It now is using the conjugate of h, but it still is using a Bregman divergence, and it's not using x dot anymore. It's now using this new conjugate variable p. But otherwise, it's very, very similar to what we had before. So you might expect that similar kind of things can be done with it, and we wrote that in the original paper, but really didn't do much with it. It has some other symmetries and some properties. On the other hand, it's time varying. Right, and usually in physics, Hamiltonians are not time varying, and you get these limit cycles, and things are conserved, so on and so forth. Right, but you can work with Hamiltonians which are time varying, and what you basically do is you turn it into in a bigger space an object which is not time varying. You introduce t as an explicit variable, and you give it a conjugate variable, which is often called the energy. And you add those to your space, and now you can work in a bigger space where you have a Lagrangian. So why do I bring all that up? Well, when you start talking about discretizing these kind of things, what is called symplectic integration starts from the Hamiltonian perspective. And Hamilton himself worked on this. Like, I now tell you what the problem that he was working on, which is he and others solved, which is very important. So they were looking at differential equations gotten by classical mechanics. And so think about the cosmos. You're trying to simulate the cosmos. Well, you have some differential equations. If you could solve them exactly, you would move along orbits in a phase space such that things were conserved, that the physics tell you are conserved. Energy, momentum, and some other things conserved. In general, what are called exterior forms are conserved. So they studied a lot of those, the geometry of those objects. But then they asked a really interesting question, which is, well, what if I discretize those differential equations of the cosmos or of a protein or whatever? I will get out a set of difference equations, and I will now hop along, and hopefully I'll hop along close to the original path, right? Can I make that error small? So, but here's the interesting question. As I'm hopping along, what's happening to the energy and the momentum, right? Well, in general, they would be approximated. And it could be that they're approximating kind of not a great way, that you're bleeding away energy or momentum. They're going off to something. So you would not be doing physics anymore. You're doing something wrong. And your inferences would probably not be so good. So they asked, is there a way to discretize where I do get an approximate path, but I exactly conserve momentum and energy and other things? That's a good math problem. Right, and it turned out that the answer is yes, and there are now big textbooks. It was a whole field that emerged, and in modern math departments, there's still branches of that field exist in the area called symplectic geometry. Harrer et al. Is a very good book on this if you're interested. Long story short, what turned out to be the right way to think about this was that as you're discretizing a flow, instead of just looking at a point and looking at the gradient and then moving along that, what you think about is a little triple of vectors at that point. Right? Adds like an indeterminate, a little triple. And you want that triple to flow along the flow line, right? And you allow the triple to shear and change shape, but you want the volume of that thing to stay constant. Okay? So this little triple is kind of shearing in complicated ways, but the volume is staying constant. So there's nice pictures where you take a little cat, and you sit the cat there, and the cat shears in a complicated way. The overall area or volume of the cat is being conserved. Okay? So you can now write that down as a mathematical statement. I want a little, basically, determinant to stay constant as I evolve, right? And determinants are alternating pluses and minuses. So this leads to this area of symplectic geometry where you don't just have pluses, you have pluses and minuses. So they worked it out and found out a way to do that. Now, since we don't know what we're trying to conserve here, this seems not all that relevant. But here's the key part, which is that as you develop these symplectic integrators that do conserve these three things, and just again to say what they turn out to be, they turn out to be a combination of an explicit step, given the gradient here, I hop, plus an implicit step, given the gradient out there. How do I achieve that? You put the two together, those are what these integrators do, right? When you do that, you turn out you can make much bigger steps and still have a good approximation to the differential equation. And the whole overall system stays much more stable. So the intuition is that because I have this triple staying constant, there's kind of a tube around the flow in which I'm stiff, I'm stable. I've really strained the thing a lot more than the classical stuff. I could just kind of head off. So I get to make much bigger steps. All right, so long story short, people in physics who do like the cosmos simulations or climate or proteins or whatever would never use classical discretization methodology. They always use symplectic integrators. And there's a whole, each one of those fields has its own symplectic integrators which are taken out to higher orders. There's a whole literatures on that. So it's a huge area of really vast importance. Okay, so given all that, can we start with our Bregman Lagrangian and see what happens if we try to symplectic integrate? Okay, so I just said all this stuff. Okay, so first of all, we have to start from our Lagrangian. We go to a Hamiltonian. We add a couple of variables to do that. Instead of having these kind of derivatives around, we have a bunch of others. Let's not worry about these kind of details. But now let's try to use these. So here's just for a particular system of differential equations. I don't even remember which one. Here's with a small step size. Here's a larger step size. You can see we're kind of converging faster. If we go to too much, too ambitious, we get something unstable. Here is the symplectic integration of the Bregman Hamiltonian. Okay, so here it is. That slope there is that worst case rate. That is the 1 over a squared rate. Okay, which is achieving. And it is oscillating. It's not a descent method. So in some sense, we now know something more about these oscillations. Okay, is that Nesterov acceleration? That would, for a little while, I thought that was it, and we had just kind of put quite a paper saying Nesterov acceleration is symplectic integration. All right, that turned out not to quite be true. So this new procedure is different from Nesterov. It is as effective as Nesterov early in a run. It does achieve the worst case rate, but it's slower near the optimum. So what Nesterov actually ends up doing, show you a picture here, is that Nesterov goes down for a while, and he it gets a little better near the optimum. Right? So, all right. So what Nesterov is actually doing, and so this is a bit of a mystery, this part, but momentum is really good when you're far from the optimum. Okay, and so Nesterov and other momentum kind of based methods are really important when you're far from the optimum to kind of pick up a lot of momentum and get into the place where it matters. So for a lot of our learning problems, that's kind of already enough. If you're getting close to the optimum, you can stop and you're done. Right? But if you keep going, the momentum starts to hurt you because you oscillate, you slosh around too much. You want to converge. So at that point, you'd like to kind of just do gradient descent. So that's not going to slosh around too much. So what Nesterov is somehow intuitively doing is that he managed to come up with an algorithm that has a little bit of both. It has a momentum, but the momentum part goes away, and it's just this gradient that's in at the end. All right. So we said, well, can we mimic that? Right? And we still don't have a principle. This is now where we're kind of being a little ad hoc. But here, so let's just do gradient descent. I've already told you that's like gradient flow. So here's a gradient flow equation. So let's now just mix the two. Okay, just add gradient flow plus our stuff that we've been doing and symplectically integrate. All right. So when you do that, you get this thing right here, which goes down, adds the gradient thing, and the gradient thing helps you near the end. Okay. So that is an existence of one of the best. That and Nesterov are the best algorithms known. Okay. Here is a comparison of them head-to-head about 4 months ago. And so the symplectic one was showing that it was a little bit better early on than Nesterov. And I didn't get the slide. Mike Betancourt did this simulation, and I'm going to get him. Maybe I'll get him tonight to do it. We managed to get the symplectic mix to shift over quite substantially. It's now about a factor of 10 faster. Okay, just by doing something. All right, so that's where I'm going to stop. Symplectic integrators, now what is beautiful here is that we wrote down our Bregman Hamiltonian, we just symplectically integrated it in a classical, beautiful way, and it works. It is achieving the optimal oracle rate, and it's stable. Okay, so that is a great part of the story. Now the new mystery is that near the end, it's not the right thing to do. The Bregman, it's not that symplectic integrator is not the right thing to do. It's that the Bregman Lagrangian is not the right thing near the end. Okay, so if you in an ad hoc way add in gradient flow at the end, then you get the best of both worlds. Right? But we have no principled basis on doing it, nor did Nesterov. So this is now an interesting new mystery. We have algorithms now, and they're kind of more principled than they were before, but they're still an ad hoc near the end to actually get best algorithm. So that's all I wanted to say for this morning's talk. I'm happy if there are a couple follow-up questions now. I know you're hungry. I am actually, but are any burning questions? I'll also happily take advice for what else to talk about. I'm probably going to go back and look at what else you've learned about this last 2 weeks and make sure that I cover things I think you should know that it hasn't been covered. If any of you want to scan my publications page and look for stuff, I'd be happy to talk about it if you want. Sure.
Otherwise, try to follow him to punch. Thank you. Okay, thank you very much.